Welcome to our presentation. This is Haoming from Amazon and the Georgia Institute of Technology. Today I'm going to present our work towards automatic evaluation of dialog systems, a model-free off-policy evaluation approach. This is a joint work with Bo, Mengjiao, Tuo, and Wei. Dialog system is one of the ultimate goals of artificial general intelligence. This is an example of a chatbot for automated flight reservation. One fundamental question is how do we measure the performance of dialog system? The most ideal approach will be human evaluation, which is essentially an online reinforcement learning setting, where we evaluate an agent or policy in a real environment by keeping humans in the loop, and humans provide both responses and rewards. This is also called a Turing test. However, such Turing test is neither practical nor affordable. So some automatic evaluation approaches are proposed to alleviate human effort. The most popular way is static evaluation, which is also called single-turn evaluation. In single-turn evaluation, the model is given some fixed dialog history and try to make some response. And then we compare that response with the real human response. For example, we can use perplexity and blue score. However, such static evaluation methods have a lot of problems. The errors may compound when the real interaction between human and agents drifting away from the dialog history. It fails to capture the interaction between human and agent, and it cannot reflect the human experience well. The other promising approach is called offline reinforcement learning-based re-evaluation, where we ask several behavioral policies to chat with humans and generate many conversations as the experience data. And then we apply offline RL modeling on this experience data to evaluate a new target agent. Existing offline RL-based evaluation approaches are mostly model-based self-play evaluation, where we train a model to imitate a human evaluator. And then we also predict the reward with some handcrafted features. So what is the downside of the model-based offline reinforcement learning evaluation? Actually, the human customer is very difficult to imitate, and the reward function is very difficult to predict. So the model-based approach can be inaccurate. So in this paper, we investigate a model-free offline policy evaluation approach. Our proposed solution is called Enigma. Enigma first applies pseudo-state padding to convert a dialog into an infinite horizon Markov decision process, such that we can apply offline policy evaluation methods. And then we could apply the state-of-the-art offline policy evaluation method, which is so-called DICE. DICE represents distribution correction estimation. It is model-free and behavior agnostic. We can also stabilize the training of DICE by using normalization and regularization. To further improve the performance, we use function approximation with pre-trained language models, such that we can transfer semantic and synthetic knowledge through continuous latent representations. To begin with, we formulate dialog generation as Markov decision process, where we have the state space contains all possible dialog history, and action space contains all possible agents' response, and the transition kernel is defined by the environment, which is a human behavior here. And human evaluator will measure the quality at the end of the conversation, which is a sparse reward. And we also have the initial distribution, which describes the customer's intent or maybe the knowledge base in the dialog systems. The agent evaluation can be described as a value estimation problem under the RL context. For online evaluation, an agent can be evaluated by its expected reward defined as rho pi here, where H represents the conversation generated from sampling the interaction between the target agent and human beings. So for offline evaluation, we aim to estimate the rho pi based on pre-collected experience data. The pre-collected experience data are generated from behavior policies that are different from the targeted policies. So we first apply pseudostate padding to the dialogues because most OPE methods usually assume an infinite or fixed horizon, while the dialogue may have varying horizon. So we turn the varying horizon to an infinite horizon via the padding and augmentation. The augmented MDP has very nice property. It has a unique stationary state action distribution, and the policy value of pi is proportional to its counterpart under the original MDP without augmentation. And then we can apply dice method. The dice method essentially decomposes rho pi into this formula, which enables us to sampling from the experience data instead of sampling from the real interaction. So we introduce an additional term here. It is called density correction ratio, which is the ratio between the stationary distribution induced by the target policy and the empirical distribution of the experience data. So DICE essentially turned the problem of estimating rho pi into estimating the correction ratio. To estimate the density correction ratio, we just need to solve this minimax optimization problem. Such a minimax formulation is adapted from the primal and dual linear programming forms of all policy evaluation. Note that the reward has been decoupled. If you want to know more detail about this minimax formulation and how to solve it, please refer to the original DICE paper. So why do we choose DICE in dialogue evaluation? First of all, it is model-free, which means there's no need for us to imitate the human customers. And it is behavior agnostic, which means we don't need to know what behavior policies are used to collect the experience data. It makes the whole algorithm more generalizable. And the density correction ratio is decoupled from the sparse reward, so we don't need to worry about the sparse reward. And we can apply regularization and post-normalization to stabilize the chaining. To further improve the performance, we apply function approximation by using Robota. It converts the discrete state action space into a continuous embedding space, and it transforms the semantic and synthetic knowledge through representations. Here are some experiment results. We did experiments on flight ticket reservation dialogue systems. The task is called Air Dialogue. We asked 10 human evaluators to chat with 24 different agents and collect the experience data of 2,400 of conversations. And we evaluate Enigma under leave one bolt out evaluation protocol. More precisely, when evaluating each agent, we used 2,300 of conversations of the other 23 agents as the experience data. To evaluate the performance of Enigma and other automatic evaluation methods, we compare their correlations to the human evaluation scores. Here we consider 3 different task completion metrics for air dialogue, including flight ticket scores, action status accuracy score, and the overall reward. As can be seen, static methods such as blue score and perplexity, they fail to correlate with the human evaluation scores. The model-based self-play evaluation can do much better. And as can be seen, our proposed Enigma can outperform all baseline methods. Here we show the regression plots. In each regression plot, each point representing a dialogue agent. The x-axis is the ground truth reward given by the human evaluator, and the y-axis is the score estimated by the OPE method. As can be seen, the score estimated by Enigma is more accurate than the self-play evaluation. However, offline policy evaluation is not perfect. It has its own limitations. The biggest challenge here is the coverage of experience data. We require the behavior policies to be not significantly different from the target policy. which is due to the fundamental information theoretical limit of RPE methods. This has been discussed in many RL literatures. To understand this limitation, we can consider a scenario in ticket reservation dialogues. The human agents can always book the correct flight tickets, and the reward will always be 1. In contrast, the trained agents often make mistakes. There's no way to evaluate such mistakes if the experience data are only from human agents and does not capture any failure mode. In summary, we have a few take-home messages. First, reinforcement learning for dialogue system is very promising, but yet very challenging. Model-free RL-based evaluation methods can avoid imitating complex human behaviors and improve the performance of RPE. The offline policy evaluation problem has its own fundamental limitation, which is the coverage of experience data. So we call on the broader research community to release human-agent interaction evaluation data to promote research in RL for dialogue systems. These are the reference and the QR code for our paper. That's all for my presentation today. Thanks for coming. If you have any questions or if you want to discuss anything related to the paper, please send me an email. Thank you.